Good morning, students. Welcome to video lecture on electromagnetic waves and transmission lines. Subject code U18EC403. Topic: energy stored and energy density. Energy stored are represented by capital W subscript E. The units are joules. Consider an empty space. Empty space means the electric field is zero and potential is zero initially. Consider 3-point charges Q1, Q2 and Q3 present at infinity, and suppose we wish to transfer these charges into empty space one after another at points P1, P2 and P3. Uh, we are supposed to transfer these point charges one after another, Q1 at P1, Q2 at P2, Q3 at P3. And after transferring, we are going to calculate the energy stored in the system. The transfer of charge is first we transfer Q1 followed by Q2 followed by Q3. The energy stored or work done is simply the product of potential and charge. Based on this base equation, we are going to calculate the amount of energy stored in the system. Initially, the system is empty space. In empty space, the Q1 charge is transferred, and in empty space, the potential is zero. The amount of energy spent in transferring Q1 charge is zero. Plus, uh, in the second attempt, Q2 charge is to be transferred. At the time of transferring Q2 charge at P2, the Q1 charge is already transferred at point P1. So it is multiplied with potential at 2 due to Q1 charge, plus the next is Q3 charge is to be transferred, and at the time of transferring Q3 at P3, the Q1 and Q2 charges are already present in the space. Means some amount of potential will be present at point P3 due to Q1 charge and Q2 charge. That is potential at 3 due to 1 and potential at 3 due to 2. Let it be equation 1. Now reverse the order of the charges. Q3 followed by Q2 followed by Q1, and in empty space Q3 amount of energy required to transfer Q3 is 0, and Q2 is to be transferred. At the time of transferring Q2, Q3 is already is in the space, means potential at 2 due to 3, plus after transferring Q2 and Q3, we are going to transfer Q1 charge. The Q1 charge potential at 1 due to 2 and potential at 1 due to 3. Let it be equation number 2. In the next slide, we are going to add equation number 1 and 2 to get equation number 3. Let us continue our discussion in the next slide. 2 into WE. By adding equations 1 and 2, we get equation 3. 2 into WE is equal to Q1 V12 V13. Potential at 1 due to 2, potential at 1 due to 3, plus Q2 V21 plus V23. That is potential at 2 due to 1, potential at 2 due to 3. And in the same way, Q3 V31 plus V32, equation 3. And this can be written as Q1 potential at 1 due to 2 and potential at 1 due to 3 replaced by V1, and in the same way Q2 V2 plus Q3 V3. 2 into double the energy stored, and WE is equal to half into Q1 V1 plus Q2 V2 plus Q3 V3. And the generalized equation for n number of point charges is summation k is from 1 to n qk vk. It is equation 4, and equation 4 is very important in solving problems. And once again, let us continue our discussion with equation number 4 in the next slide. Remember equation 4. Energy density represented by small w subscript E. The units are joules per meter cube. Instead of point charges, if the region has continuous distribution of charge, then equation 4 becomes energy stored in the system WE is equal to half into integral of rho L V dl is equal to half into rho S V ds is equal to half into rho V V dV. It is 5A, 5B and 5C. Consider 5C, that is energy stored is equal to half into volume integral of V dV. Here capital V means voltage, volume, and from the Gauss law, the differential form of Gauss law, del dot d bar is equal to rho V. Equation 6. It is one of the Maxwell's equations. Now we rearrange 5C in terms of 6. Energy stored is equal to half into rho V is equal to del dot d V of dV. Let it be equation number 7. And from the calculus, we know the identity del dot V of V d bar is equal to V of del dot d plus d dot del V. Equation 8. And V of del dot d is equal to del dot Vd minus d dot del V. Now substitute equation 9 in 7, and let us continue our discussion in next slide. Now it becomes the energy stored is equal to half into volume integral of del dot V d dV minus half into volume integral of d dot del V dV. Equation 10. This can be written as half into, by applying divergence theorem, it will become closed surface integral of Vd dot ds minus half into d dot E is equal to minus of del V. So this can be replaced by minus V, and the plus minus minus gets cancelled. It will become plus, and let it be equation 11. And in equation 11, in first term, the V varies with 1 by R, D varies with 1 by R square, Vd 1 by R cube, and ds varies with 1 by R square. Means for a large surface, the first term will be equal to 0. Then the energy stored is equal to half into volume integral of d dot E dV, equation 12. And now differentiate equation 12 with respect to volume, that is dou WE by dou V. Partially differentiating with respect to volume, it will become half into d dot E, and it is equal to the energy density. The energy density is small w subscript E. Units are joule per meter cube, and it is equation number 13. Once again, I will rewrite energy density is equal to half into d dot E. The units are joules per meter cube. And the relation between energy and energy density. Energy is in terms of joules. Energy density is in terms of joules per meter cube. So determine the energy stored in the system. We can volume integrating energy density to get the energy stored in the system. I think you are clear about energy stored and energy density in the system. Refer to sample problem. Here, 3-point charges are given Q1, Q2, and Q3 with position vectors point P1, P2, and P3. We are supposed to calculate the energy in the system. You can follow the energy stored in the system. The equation is half into summation k is from 1 to 3 qk vk. Here v1 potential at 1 due to q2 q3 charges, potential at p2 it is due to q1 and q3 charges, and potential at 3 is due to q1 and q2 charges. Substitute the parameters to get the final solution. Refer to practice problem. Here 4-point charges are given. Initially an empty space is present, and q1, q2, q3, and q4 initially they are present at infinity. We have to transfer q1 at p1, q2 at p2, q3 at p3, q4 at p4. The points are given p1, p2, p3, and p4 are given, and we need to calculate. Here the space is empty initially. We need to calculate the energy stored in the system in such a way that by transferring each charge one after another, after transferring the amount of energy stored in the system, after transferring q2 amount of energy stored in the system, transferring q3 the energy stored in the system, and at the time of transferring q4 the energy stored in the system, like that. We have to transfer the charges one after the another, and we are supposed to calculate the energy stored in the system at the time of transferring each charge. Thank you. We will meet with the next lecture.